Welcome, math lovers. Today we will see certain properties regarding the most famous Pascal triangle. So, Pascal triangle consists of rows of numbers following a certain definition. Its input starts like 1, 1, 1. So, every row, the number of elements will keep increasing. So, in this row, and also Pascal's triangle, we start calling the row number starting from 0th row. So, this is actually 0th row, and this will be first row. Okay, so and we keep writing 1 continuously like this in a diagonal manner. Now you identify 1 plus 1, 2, that should be written here. So the second row is having 3 elements, and now 1 plus 2, 1 plus 2 is creating 3, 1 plus 1 created 2, 2 plus 1 as well as 3, 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4, 1 plus 4, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, 1 plus 5, 6, 5 plus 10, 15, 10 plus 10, 20, 10 plus 5, 15, 5 plus 1, 6. So now you identify that in every row, the number elements are adding up to powers of 2. Here in the zeroth row, the value is 1, which is nothing but 2 power 0. Here if you add 1 plus 1, you get 2, which is basically 2 power 1. Here if you add 1 plus 2 plus 1, it becomes 4, which is 2 square. It becomes 1 plus 3 plus 1 becomes 8, which is 2 cube. And this becomes 16, which is 2 power 4 and so on. So from that we understand, based on the row number, we are going to get the sum of those elements as raised to the power of 2 raised to the power of row number. So this is zeroth row. That's why the value of the elements is 2 power 0. This is first row. That's why sum of elements is 2 power 1, so on. So from that we can generalize. The first thing from this is sum of elements in nth row is given by 2 power n. Okay. And until the fourth row, you can identify they look like powers of 11. Okay, that's the second observation that we are able to make from this Pascal triangle. Until fourth row, when elements are read together, they look like powers of 11. You can read that with me. It's 1, which also looks like 11 power 0. Here it looks like 11, which looks like 11 power 1. This is 121, which looks like 11 square. This is 1331, which is 11 cube. This is 14,641, which is like 11 power 4. Until the 4th row. After that, that property doesn't work. But until that, it works like this. And Pascal triangle is also a significant importance for all the values of NCR. Now I'll explain you what is NCR. So N seems to be the number of available options. Okay. N is like the number of available options. C is like choosing or number of combinations. We can remember it as choosing. And R is like restrictions. Number of restrictions. Like how many to choose from. Okay. So for example, this particular element here is belonging to the second row. Okay. And in second row, we will start like from two available things. We are choosing nothing, 0. 2C0, the value is 1. This is 2C1, the value is 2. This is 2C2, the value is 1. Okay. And just imagine you are in a shop. You wanted to buy some 2 dresses out of 5 dresses. So we do that shopping in 2 different ways. Either you try to keep selecting or look out for those two things that you want to select, or you will try to reject the remaining three things. So they are both same, right? So we can, that logic tells us indirectly from n available dresses, you choosing R dresses is going to be same as rejecting the remaining dresses. NCR will be same as NC n minus R. So now I'll teach you how to numerically calculate this NCR. NCR is given by n factorial by R factorial into n minus R factorial. So factorials are defined for whole numbers, and starting from any given whole number, you need to write them in the descending order until you reach 1, and that product is called as factorial. Example 5 factorial will be called as 5 into 4 into 3 into 2 into 1, which is 120, like this. And there are interesting patterns in this. So one of the patterns in this is, if you take any particular elements like this, for example, I'm taking these two elements, 3 plus 3, it becomes 6, that is this. So, but this belongs to the third row. This is 3C0, 3C1, 3C2. So you identify as an example, 3C1 plus 3C2 is becoming 6, which is actually in the fourth row, 4C0, 4C1, 4C2. So we can generalize this as a property. That is, if you take NCR plus NCR plus 1, that is adding two consecutive elements of a particular row, then you will be getting the element value, which is of the next row, that is n plus 1th row, and you see this position. So the same position, n plus 1, C, R plus 1. It's a very, very important property, and it will be used in most in progression and series questions created through binomial coefficients also. You have to remember that. And now look at the next interesting property. If you add the alternative positions, what happens? For example, I'm taking this row, 1 plus 6, 7, 7 plus 1, 8. And the other positions, 4 plus 4, 8. So they were adding up to equal values, which is half of the total summation. Okay. So now, for example, look at this. I'm taking that was a fourth row. Now I'm also showing in an odd row. 1 plus 10, 11, 11 plus 5, 16. And here 5 plus 10, 15, 15 plus 1, 16. So that also is a property we can notice. Sum of odd questions and sum of even questions in nth row will be equal to 2 power n divided by 2. So clear, people? I hope this will be helpful for you. And this is one of the prerequisites of permutations and combinations chapter as well. I'll meet you with more supporting questions on this topic. Thank you all.